Hello and welcome to this 30 mechanical minute session, virtual content for real-time professionals. This session is airing for the first time at the Modern Hydronics Summit 2021. My name is Doug Picklick. I'm the editor of HPAC magazine, and I'm here today with Steve Goldie, a regular contributor to HPAC and a hydronics specialist with Next Supply, and Nico Pellegrino, technical sales specialist with Thermo 2000. Hi, Steve and Nico. Thanks for joining us.
Thanks, Doug, for having us.
Thanks for having us. Yeah.
All right. So we're here today to talk about how buffer tanks can be used to optimize the performance of hydronic system design, something you both have a great deal of experience with. Steve, I know you're a fan of buffer tanks. In a previous 30 mechanical minute session we held last year on the topic of combi boilers, you made that pretty clear. So maybe you can start just telling us the function of a buffer tank and why they make so much sense in system design.
Yeah, I've been a proponent and a big fan of buffer tanks for many years now. I like to call them the boiler's best friend because, in my opinion, I don't think there's the addition of a buffer tank will make every boiler system better, and it makes a boiler happy. It makes a boiler run better. It makes a boiler run more efficiently. And it makes boiler happy. So that's who doesn't want a happy boiler? It's a good thing. And fundamentally, what it does, how it works is it creates what is called a buffer tank. It creates a buffer, or they're sometimes called mass tanks. They are mass, which is weight or water, a lot more mass, which gives the boiler something to heat up in essence. And one of the dirty little secrets of our industry, that I call it, is short cycling. We like to design very efficient systems. We have modulating boilers. We want to make things that work very well and efficiently, but there's limitations to that. And any combustion appliance, whether it be a boiler or your car, anything that burns any kind of carbon fuel, they all work better and they all work more efficiently when they work in their full state. When they're working hot, when they're running hot, basically, in their full state efficiency, we call it. So you don't jump into your car, or a truck driver doesn't jump into a big diesel truck, start it up, and drive off. If you notice, when they start them cold, they start them up and they let them run to warm up and heat, because that's when they're going to run efficiently. A boiler works the same way, but in our systems, our boiler is designed to come on and off in response to loads. And as a thermostat clicks on and a heat demand comes, the boiler comes on. And if the boiler is doing multiple things, it's probably going to be oversized for just one little job. So the boilers will come on and go off very quickly. And what a buffer tank enables is lets the boiler run and get into that full state efficiency by running warms up, runs and modulates into a nice level area. And the buffer tank lets it do that because it doesn't short cycle and turn off, because if it's making heat faster than we can use it, it's going to turn off and on again. We call that short cycling. The buffer tank is like a flywheel. It gives it a load that it can work and heat up and run beyond longer and then be off longer, which leads to greater efficiency.
Okay. Nico, we got a picture of a system here. Maybe, I don't know if you can just tell us, I don't know if you can add to what Steve had to say just about what makes buffer tanks optimal for hydronics solutions.
All right. So basically, Steve said some great points on why it's important, especially today's world of condensing boilers and low firing and so on, and the micro and mini loads that are happening aren't good friends to boilers. And so basically, thermal mass has been around for as old as I am, as you say. And the old days of big fat headers used to be the way of kind of making for buffer tanks or low loss headers, whatever. So we just kind of made it into a better system where you're taking all that energy, and as Steve said, you're storing it and you can utilize it later on. Now that doesn't only just work for fossil fuels, it works for wood boilers. It works for heat pumps today, geothermal, anything that makes thermal mass is a buffer tank is their best friend.
Okay.
Agreed.
And here's an example. I think this is a geothermal example. Now, hooking up these to why these make so much sense for low temperature systems. Is that right? So air to water heat pumps or geothermal?
Yeah, because again, you know, you want to take advantage of the COP that you're getting out of your heat pump or out of your geothermal, and you want to be able to utilize that energy that it's making later on or as it's needed. And because it's a lower temperature, you want to store as much of it uh, so that you could take advantage. And again, as Steve said, that runtime between your heat pump and your geothermal is reduced, and it's taken, and it takes advantage of when it's getting that cold return, so that it's giving you that high COP from the unit.
Okay.
Yeah, the other point I'd like to make there is, you know, it just makes sense. If you've got an appliance, whether it be a boiler or a heat pump or whatever, it's making heat, or it may be cooling in the summertime. It's basically, you know, moving energy. Now, and the demand of our on the other side, where we're distributing that heat or the cooling, that varies. On a cold day, it might be, you know, you've got, you know, even if it's a single zone system, but if multiple zone systems, it amplifies the problem. But how much heat or energy you're drawing varies. As it gets colder, you need more heat. As it gets milder, you need less heat. So that demand is changing. It's going up and down. And I've got an appliance on the other side. In the old days, I had an appliance that basically could be on off. It made heat at one rate. Now, so if it was 100,000 BTU boiler, it only made heat at 100,000 BTUs. Now we have modulation, which is a big improvement. So I can try to modulate, and okay, I'm going to match how much heat I'm making to how much heat my system's taking out. Well, that sounds like a great solution, and it works quite well, but it's complicated to say, okay, I'm going to now get my boiler to produce as much heat as my system's taking out. And how does my boiler know that? And so we do outdoor reset, and we try to guess at that. And that's great. But again, my boiler comes on, it's trying to match that load, and then my heat load's taking load, which is always changing. It's like a moving target. So it's very difficult to get an appliance that can keep up with that. So the buffer tank is exactly what it says. There's a buffer in between those two things. So the buffer tank allows me to, you know, store that energy and let the boiler, it doesn't have to be always trying to, you know, adjust to try to keep up. It can do its thing, bank the energy, and my system can do its thing. It can draw the energy as it needs it. And that buffer tank sits in the middle. It takes energy as the boiler's going, as much as you want to give it, and it releases energy as much as you want to take away from it. And it just is that happy place in the middle where it's receiving and giving the energy one way or the other. And it's the bigger the better, in the sense, the bigger it is, the more capable it is of doing both of those things very well.
Okay.
Does that make sense?
Yep. Now I've heard, I don't know if the contractors need to know about connecting buffer tanks. I've seen 2-pipe, 4-pipe systems. Maybe you can, Nico, can you address that?
Yeah, I mean, there's been an ongoing trend now that, you know, utilizing a buffer tank to its fullest, right? I'm old school. I think Steve's the same as me. You know, as a manufacturer, we manufacture a buffer tank with 4 ports. You can use 2, you can use 4. If you do it right, a 4-pipe system works just as well as a 2-pipe system.
Better.
A 2-pipe is more or less more of a new way of doing things that some guys are looking at. You're satisfying your load quicker rather than pulling from the tank. Again, I'm a firm believer that 4-pipe works just as good as 2. But it's, you know, the thing about what I find in this industry is you can talk to 5 guys and 5 guys will give you a different answer. So it's all in what you find works for you. And the bottom line for me, as Steve says, make it be the friend to your boiler so that you're not having excessive repairs and maintenance or whatever the case may be. and utilize that energy that you can get from a buffer tank um,
Agreed.
to make the system better.
Yeah, I agree with Nick. The two pipe systems, I've seen them. And so, so the difference is in a two pipe system, you've got a pipe coming in and a pipe coming out the other side. So you're supplying, and I guess the one advantage of a two pipe system is it's not hydronically decoupling the boiler or the appliance from the demand side. So one pump can circulate that whole thing. But you're also now sacrificing all the potential benefits of a buffer tank, because I got water going in, water going out. So I've got this big mass of water, but a lot of it's just sort of stagnating and stratifying in that tank and not really being utilized. So I'm losing the benefit of the buffer in large part, because I'm not. So if I've got a tank on either side of my system, I've got an inlet and an outlet going. I got a loop on my boiler side with an inlet and outlet where the boiler is doing its thing, dumping the energy into the tank. And then I got two connections, at least two connections on the other side, going in top and bottom and drawing that energy out, taking my hot water out the top, returning my cold water to the bottom. It allows my tank to stratify, which again helps my domestic boiler or my condensing boiler to draw that colder water from the bottom. Now, a one tank system is going on my supply side. I'm going in and out on the supply side. I don't have a return connection. So I'm not returning that cold water to my boiler, losing that benefit. So I've got a buffer. I can dump more. My boiler can run longer, it can fill the tank, but I'm not getting all those other benefits. And as Nico said, four connections work at least as well. Well, they work better. And I like to see tanks. I can get tanks with multiple ports. I can have on the outlet side, I can have 3 pairs and different heights of the tank, which allows me to take advantage of the different temperatures that stratify in a tank. So my high temperature loads I can take off the top, my lower temperature loads I can take off the bottom. So, when you go to multiple connections, there's all sorts of great things we can do with buffer tanks.
Well, and you talk about that. I mean, these aren't just big tanks, vessels holding water. They have sensors in them. They're talking to the controller. Can you explain that a little bit?
Nick?
Yeah, so basically, as you said, it's part of the system. So you want to utilize it to the fullest. And again, we talk about it's the friend of the boiler. So there is a formula that you should use to size the one. And as Steve mentioned in our conversation, it's never a bad thing to be oversized in a buffer tank. But there is a formula, and it's all about runtime, and it's all about, if that boiler has a short cycle of 10,000 BTUs, 15,000 BTUs, whatever that is, you want to be able to talk between the storage, which is your battery, and the boiler. So, it's done by aquastats. You can turn pumps on, as Steve said, you can do multiple demands off the tank. So it's just not a tank. There is purpose to it other than being a buffer. It helps the whole system run a lot more efficiently if it's done and controlled properly.
Okay, and you talked about sizing buffer tanks. Steve, maybe you could help us with that.
Yeah, so the whole purpose, again, one of the main purposes of a buffer tank is to reduce the short cycling that can be an issue in a boiler. So when you size it, you've got, it's variable. Again, I agree with Nick when he said, most times in our systems, I teach against oversizing most of the components. We have a big problem in industry where we like to, it's human nature, I think. We want to go bigger. Let's make sure we're big enough. We don't want to be too small, so bigger is better. And I've done a lot of teaching that bigger is not better in most cases. I don't want to oversize pumps. I don't want to oversize my boiler. I don't want to oversize my piping, certainly. I'm spending too much money. And oversizing equipment often leads to negative outcomes. It can damage, or it can hurt your system. It can cause more issues in your system that are negative. Two components that I don't mind oversizing are buffer tanks and expansion tanks, which we won't talk about those today, but a buffer tank, in my mind, you can never be too big. Bigger is better when it comes to a buffer tank, but you do have to make, measure that against cost. I got to balance the biggest one I can get for my money and the space allowed. So how do we size it? We size it based on what's my desired runtime. I want to minimize short cycling in my boiler. I would say that the minimum runtime you should be ever looking for is 10 minutes. So when my boiler comes on in response to a call for heat, I want it to run at least 10 minutes before it shuts off. If it's running less than 10 minutes at a time, I'm going to call that short cycling. So desired runtime, and then you're going to look at the minimum output. So what if I've got a modulating boiler? What's the minimum firing rate that boiler can ever run at? So if I've got a 100,000 BTU boiler that's got a 10-to-1 turn down ratio, which is very good. This industry standard would used to be 5. Now we got a lot of boilers that can do 10-to-1. So that means that it can run at 10,000 BTUs. So my boiler can fire it as low as 10,000 BTUs. So that's why I want to look at what's that minimum firing rate, 10,000 BTUs. Now, what's my smallest load that's connected to that system? If I've got a if I've got a house that's got 10 zones and one of them is just a small bathroom or a small room, if a single zone is calling, that single zone might have a load on a mild day of maybe 2,000 BTUs. So if it's running at 2,000 and my boiler can only fire at 10, my boiler is making 5 times as much energy as I can take away. So the boiler is going to basically go off in its limit very quickly if I don't have a buffer. So that's what we're trying to do when we size it. We're saying, okay, what's our minimum runtime and what's our minimum firing rate? And we can go through the math as we're doing here. I can do a quick example if you like. I've just got one here on my phone I can pull up. If we're, for example, got an 87,000 BTU output boiler, the minimum firing rate is 20,000. We've got a 5-to-1 turn down ratio in this case. For a minimum runtime of 5 minutes, I want to go at least 10, so we're going to double this. The smallest zone is 2,000 BTUs. We go through the math, or the math here. You've got your desired runtime, 5 times 20,000, which is your minimum firing rate, minus 2,000. So 10 times 500. And we divide that. And we basically, you go through that math, your delta T times 500. Which is the delta T is your minimum heat transfer, the minimum difference in your tank temperature that you want. You go through all that math, and in this case, with this very small boiler, we're looking at a buffer tank of 18 gallons, so a very small buffer tank. So it's all about doing the math, and the formula is right there. If you go through your math, I would say that we want to have at least a minimum runtime of 5 minutes. So by doubling that runtime, there's a direct correlation in my size of my tank. I would actually be doubling that size of my tank. I would want to see at least a 36-gallon buffer tank in that small example we gave there. So okay. Yeah, I hope I didn't confuse too many people. But the math can be daunting, but it's basically following it step by step, and it's very simple to do.
Now, I wonder if people do get confused. I know I did. The difference between a buffer tank and an indirect tank. Maybe, Nico, you can start and Steve jump in.
Yeah, so, I mean, they are two different equipment. So an indirect is basically, it produces domestic hot water through indirectly getting boiler water from it, and it makes domestic water, but it really does nothing. The typical buffer indirect does nothing to be like a buffer for the boiler. So the buffer tanks is more the friend of a boiler, where the indirect in the market is more of a load other than a helper.
Right. And if I can jump in there, a buffer tank or an indirect tank is doing one load, a domestic water load. Now, a domestic water load is a load that is what I would call buffered, because typically your domestic load is when my tank needs heating up. If I've got a 60-gallon, 80-gallon water tank that needs heating up there, once that gets down to temperature, as long as my differential is large enough, my boiler is going to come on and it's going to get that long run time, because it's got a lot of mass to heat up. So the domestic load itself is a buffered load. So some people think, well, my indirect tank is a buffer tank. Well, no, it's not. My domestic load is a buffered load. So if I'm just doing domestic, I don't need a buffer tank, because the indirect tank, the domestic load, is a buffered load. But when we're talking about a buffer tank, we're talking about for the heating side, where I've got multiple heating zones. And a typical indirect tank doesn't do anything to buffer my heating load, because it's piped separately. It's a one load off of my heating tank, off of my heating boiler. And most boilers will shut off and do domestic priority. They'll focus all their energy on doing that domestic load and turn off the heating when they're doing domestic. Doesn't give me any buffering for my heating load at all, unless there is a product out there that kind of combines both. It will make domestic very efficiently, very quickly, because it's basically the opposite of most indirect tanks. Most indirect tanks have got a stored mass of water with a heating coil in them to heat from the boiler. There is a product out there that's the opposite. It's a stored mass of boiler water, which heats water through a coil indirectly. And that gives me the benefit of I've got a stored mass of heating water there, not domestic water. I've got a stored thermal mass of heating water, which now heats my domestic water very quickly. While now I've also got a built-in buffer tank right there. And I've used that type of tank in many designs, because now I can put separate tappings on there, and the company does make it that way, that now I can draw that heating water and do my heating loads. And the beauty of that tank is now it simplifies my control. I don't have to have my boiler separated and have domestic priority, because now I'm putting all of my BTUs all the time into my thermal battery. And now I just have to I draw that energy where I need it when I need it. When I need domestic, it's doing my domestic automatically. When I need to draw off heating, it can draw off a little bit or a lot of heating without cycling my boiler. My boiler now does not come on in response to a heating. A thermostat clicks on, my boiler doesn't have to come on. It doesn't even have to know, because all that's going to happen is a pump is going to now start to siphon energy off of that mass tank, and the battery is there. It's going to start draining energy from the battery. And the boiler is only going to come on when the battery gets to the point where it says, oh, I need more charge. And that's the control strategy. There's a sensor in there that says, hey, boiler, charge me up. I need more. Boiler comes on, says, okay, happy to do it. And it runs, chugs away for a nice long runtime and turns off again. Boiler doesn't have to know what's going on in the system. It's one of the things I love about the buffer tank. And if you can combine those and do your indirect water, your domestic water as well, beautiful.
Well, that kind of covers, I think the next question I had had to do with limited space. I think in residential mechanical rooms, I'm sure you've all heard that before. The space is limited. So how do you make room for a buffer tank? How do you accommodate that?
Well, I mean, as we keep saying, the benefits of a buffer tank, you also have to look at, there is an added cost, obviously, but you have to let the consumer know that it's part of a system that will make their system run a lot better with less problems. And, I mean, I see it a lot in commercial. Our mechanical rooms are getting smaller and smaller and smaller, because real estate is expensive, right? Everybody wants a bigger room, their family room, their theater room, whatever it is, but they want to be able to have a mechanical room that's going to work. So basically, when I was a contractor, I really didn't give them much of a choice when it came to buffering. It was more or less, let me build a system for you that's going to be right for your application.
Right.
Yeah. You have to sell it. Like you say, how do you get the room? Well, you tell them you need the room. At the end of the day, it comes down to choices. You got to make your choices. And, the trend has been for a long time, smaller, more, we want the equipment to do more, but we want to give it less space to do it. It's so often we go to these houses, large custom homes or commercial spaces where Nick says the mechanic rooms are getting smaller. They want them to do more, but they want to give you less space to do it. Well, at some point, something's got to give. And so you got to educate the consumer, whether it be the end user and the contractor, and make them understand the implications. And if they want a system If they want a box on the wall that can, the box on the wall that can do everything. It can do my water, hot water. It can do my heating. It can do my, air handlers and my floor heat, everything out of one box. Sure, we can do that. Are we going to do all of those things well? No, there's compromises that we're making. If we want the system to work as well as current technology can make it work, then a buffer tank needs to be a part of that system. It's going to make every system better. So we need the room. Yes, it's mass. It's a buffer tank. It's a thermal mass. It means it's big. It needs space. You don't want to put it in the boiler room? Perfect. My ideal, put a 10,000, bury a 10,000 tank in the backyard or under the house. That's, to me, that's the bigger the better. So you bury a big tank, insulate it, you got the insulation of the ground, and then you can spend, put a solar collector on the roof now and take all that sun energy. Whenever the sun shines, take as much of that energy and put it in that battery. The bigger the battery, the more different ways you can pump that battery full of stored energy. Right. And there's all sorts of things we can do with it. But how do you make room? You educate the consumer, and they have to make the choice. Is that what they want, or do they want to make compromises and save space and have an extra row of seats in their home theater? I don't know.
Nico, what about maintenance of a buffer tank? I mean, is it just plug and play? I mean, what?
Well, it is plug and play to a point. Again, it actually, again, enhances a system because, as Steve keeps saying, bigger is better. There's more room there. I mean,
only
again,
a buffer tank. I don't want to be accused of saying bigger is better.
No.
Except for buffer tanks.
Right. That's what I'm saying. Buffer tanks, right? So when you look at the buffer tank, it acts as we said, a hydraulic separator. The new trend now is magnetic strainers to catch any minerals and metals that are in systems. So basically, it has somewhere to go, and the tank will help you there. Eliminate air. So with automatic air vents on the unit, it will eliminate air from the system. Help again because you're accumulating a mass of water, a lot of sediment. That's why drain valves should be at the bottom of the tank. And if a thing about hydronic systems, you don't want to drain them. You just want to maintain them. And I'm a firm believer, if you get it right the first time you install the system, you get all the air out, you get everything done, put your mags in, everything that needs very, very little. It's a closed loop. It's what I call just heating water. That's all it's there to do. The least amount of times that I introduce fresh water, the less problems I'm going to have.
Oh, absolutely. Yeah. There's still some people believe out there that it's a good thing to flush your system now and again. Put fresh water in there and clean out the bad water. No. Please don't do that. A separate topic, but let's dispel that notion.
And one more thing, I know we've talked about the buffer tank as a storage for thermal energy, and we're talking heat most of the time, but these are also can be used for chiller units, right? For the heat pump folks.
They can be utilized. Again, it's just like heating, cooling is the same when you're using water as a cooling medium, is stored energy. So you want to be able to store energy when you need it. And a buffer tank works very, very well in a chilled water application because of the fact that you have energy there when you need it. Your compressors don't have to run. Your cooling tower doesn't have to work as hard because you're storing energy. And again, the way you design the system is the chiller talks to the buffer tank, and whatever happens on the other side of the buffer tank and the chilling side of things it's a whole different ball of wax. The thing you have to remember is, the insulation and dew point and condensation is the enemy of a chilled water system. So if you're going to stick this thing in a really hot room, make sure that it's well insulated and properly drainage and everything else, because it can cause havoc if the dew point and the tank will fail prematurely.
Yeah, if you're filling a big, if you fill a glass with, on a hot, humid day in the summertime, fill a glass with cold water, what happens on the outside? You get condensation. It
Yeah.
draws that moisture out of the air and it clings. Now, if you got a big steel tank as a buffer tank, that's a chilled buffer tank, and it's full of chilled water, it's going to be a magnet to that condensation in the air as well. So what happens with steel when you put water on the outside and oxygen, it rusts. So they need to be insulated, and insulation is even more critical. Insulation on a heating buffer tank is good to keep your heat and your energy where you want it. So we want to have insulation on our buffer tank for a heating buffer tank. On a cooling buffer tank, yeah, we want to keep the energy where we want it, but even more than that, we want to prevent condensation from building up, which will cause rust and corrosion and shorten the life of our. So when you talk about maintenance on a chilled water buffer tank, the maintenance is making sure that tank is insulated. You don't get what we call, if you've got separation in your insulation and you get air in there, you could get a pocket underneath your insulation jacket that is going to be prone to insulation, and that's going to be a rust spot within no time. So, the maintenance on a chilled water tank, buffer tank, is probably more important than on a heating buffer tank.
Okay, good to know. Guys, I think our time's just about up, but
Well,
Nico,
just got started.
I know. Nico, I just want to ask if you have any final comments, anything else you want to say? Buffer tanks.
Again, as we mentioned, in my contractor days, even the day before, I'm going to put my age here. I was doing systems before the condensing boilers came to market. So I was always a firm believer of, if I'm going to spend money and heat water, I'm going to save it so that I can use it down the road. And with today's world of, we're trying to save the environment and everything else, I want to let my fossil fuel equipment run as least as possible, but utilize the energy as more as possible.
Yeah. Steve, final thoughts?
Yeah, I can't stress enough how, I've seen, again, from years of experience, going back to old Scotch Marine fire tube boilers that were filled with hundreds of gallons of water. They didn't short cycle, and they run much more efficiently. Even old ones that are 80 years old now that are in apartment buildings run better than a bank of low mass copper fin boilers every day of the week. And I've seen that from firsthand knowledge. I'm not talking about condensing, but the buffering capability of a lot of mass of water increases efficiency of any boiler. I don't care if it's condensing or not condensing. A buffer tank buffering makes every boiler better, period.
There you go. Buffering makes every boiler better. You heard it here. Guys, Nico, Steve, thank you very much for your time today. And thank you to everyone who's watching.
Thanks,
Thank
guys.
you. Bye-bye.
Bye.
Bye, guys.